So in this lecture, we're going to look at some integral results. Why do we need these results? Eventually, we want to solve the solutions of the heat equation or the wave equations, and the solution depends on something called the Fourier series. And the analysis of the Fourier series depends on some integral results. And you will see later on, not only in this lecture, but also the next lecture, why we need these results at all. Before we get to the integral results, I want to give you some definitions about the even function, the odd function, periodic function. So this type of definitions related back to psi function and cosine function. So even function are function of the form f of negative x equal to positive f of x. And graphically, the uneven function is symmetrical with respect to the y-axis. Some of the example that you have seen many times already, which is parabola, so x squared, the power function x to the 4th, the power function x to the 6th power, or in general x to the n for even integer n. So you have x squared, x to the 4th, x to the 6th power, or x to the n for even n. Okay, or cosine of x and cosine of n of x for integer n for any integer n. Right, so cosine of x, you have learned that in calculus or pre-calculus. So cosine is an uneven function and the graph is symmetrical with respect to the y-axis. Cosine of nx, when you have cosine of nx, is going to give you a different period. And we will look at the periodicity a little bit later. But foreshadowing, cosine of x is a periodic function with period 2 pi, and cosine of nx is also a periodic function, but with the period of 2 pi over n. And you may wonder, how would you get the period? It is a quick reminder that the period is calculated using the formula 2 pi over capital B, for capital B is the constant in front of x. So in the case of cosine of x, the constant in front of x is 1. So that's why cosine of x has a period of 2 pi. And cosine of nx is a periodic function with the period 2 pi over n, because the constant in front of x is n. Okay. Now for an odd function, so our functions of the form f of negative x is equal to negative f of x. Now, graphically, an odd function is symmetrical with respect to the origins. Some of the odd function that you have seen many times already, which is x, the linear function x, the cubic function x cubed, the power function x to the 5th power, or in general, the power function x to the power n for odd integer n. So you have x to the 3rd power, or cubic function, x to the 5th power, or in general, x to the power n for odd integer n. Now, I want to relate back to sine and cosine function. So psi function is an odd function. So psi of x is an odd function. Psi of nx is also an odd function for integer n. Okay, so psi cosine function is periodic function of period 2 pi, and sine function is also a periodic function with period 2 pi. And to find the periods, you use the same formula as I show here, 2 pi over b, for b is the constant in front of x. So sine of x is a periodic function with period 2 pi. And sine of nx is a periodic function of period 2 pi over n, because the constant in front of x is n in this case. Okay, now we know that sine is so we know about even function, we know about an odd function. Now, if you multiply two functions together, what are we going to have? So the product of two even functions is an even function. Next, the product of two odd functions is also an even function. And the product of an odd function and an even function is an odd function. Okay, so we need this type of product a little bit later for the integral results. Okay, now let's move on to another definition. This is periodic functions. So a function f of x is said to be periodic. So a function f of x is said to be periodic if there exists a positive number, capital T, such that f of little x plus capital T equal to f of x for all x. Okay. And you say that the smallest of such capital T is called the period of f of x. Okay. And graphically, the periodic functions have repetitive behaviors. A periodic functions, or the graph of a periodic function has repetitive behaviors. Okay. So we know, again, we know that cosine function not only an even function but also a periodic function of period 2 pi. Sine function is an odd function but also a periodic function with period 2 pi. Okay. Now I want to write the example. So sine of x and cosine of x are periodic function with period 2 pi. Algebraically, this is what you can describe about the periodicity of the sine and cosine function. So you have sine of x plus 2 pi equal to sine of x and cosine of x plus 2 pi equal to cosine of x. Tangent and cotangents are also periodic functions, but they are periodic function with period pi. So tangent of x and cotangent of x are also periodic function with period pi. Algebraically, this is how you can describe the function. So tangent of x plus pi equal to tangent of x, and cotangent of x plus pi equal to cotangent of x. Now, in the next example, I'm going to show you a function is rather look complicated, but it's very useful for us later on in this lecture. Okay. So the first function I want to show you is the psi function. So psi of n pi over L times x plus 2L. So in the next lecture, when we encounter Fourier series, this will make sense. This type of psi function, this type of cosine function will make sense. Okay. Now, for this function, psi of n pi over L times x over plus 2L, I would like to distribute n pi over L into the parentheses, and I get psi of n pi plus 2n pi, and this is equal to psi of n pi x over L. So doing this, I want to show that psi function is periodic function, but in this case, the period is 2 pi, right? We're going to use the same formula as I showed earlier. That is the formula 2 pi over capital B, for capital B is the number in front of x. So in this case, the number in front of x is n pi over L. So I'm going to do the calculation for the period. Right, so 2 pi over b, for b is equal to n pi over L. You divide a fraction, you can multiply by the reciprocal. So you have 2 pi times L over n pi. This is going to give you 2L over n. And in this case, we assume that n is equal to 1 to just calculate one type of period. If you have n equal to 2, then you have a different type of period. Okay, so I would like to emphasize that where n is equal to 1. So when n is equal to 2, you have the period to be L. So the distance between the two peaks of sine and cosine will get closer and closer and closer. That means you're going to have more waves in the sine and cosine functions. Okay. So that's why in this case, when we assume n equal to 1 just for the period, not for the entire functions, the psi functions that we have here is the periodic function with period 2L. And we can do the same for cosine functions. So cosine of n pi over L times x plus 2L is equal to cosine of n pi x over L plus 2n pi. And this is equal to cosine of n pi x over L. Okay. Now, moving on to integrating an odd and even function over a symmetrical domain. So let's consider this functions right here. This is an even function because the graph is symmetrical with respect to the y-axis. Okay. The idea of integrating an even functions over this interval is so that we can rewrite the full integral into some easier integral to deal with. So now I want to say the integral of an even piecewise continuous function over the interval from negative L to L is, right, so the definite integral from negative L to L of f of x dx can be written as 2 times the integral from 0 to L of f of x dx. Remember, in this case, f of x is an even function. So here y equal to f of x, and f of x is an even function. And the interval of considerations in this particular case is from negative L to L, and we call this the symmetrical domain. Okay. So technically, what you do is that when you integrate even functions, you don't have to integrate the whole thing from negative L to L. You can basically just integrate or find the area under this part of the curve, right, from 0 to L only. And then whatever the result you get, you multiply it by 2, and you get the result of the integral of the function from negative L to L. Now for an odd function, so the integral of an odd piecewise continuous function over the symmetrical domain from negative L to L is when you integrate an odd function over a symmetrical domain, the result is automatically equal to 0. So this functions right here is y equal to f of x, and again, remember f of x in this case an odd function because the graph is symmetrical with respect to the origins. When you integrate the function and odd functions, you basically calculate this regions, right, or the area of that regions and the area of this regions. And in calculus 1, there is a concept called the psi area. So the psi area for this region is a negative value. The psi area of this region is positive value. And the two regions are the same. So one negative value, one positive value, they basically cancel out. So when you integrate an odd function over a symmetrical domain, you automatically get 0. And this result is very helpful for a following calculations that we're going to have. Now, again, I want to emphasize that this interval of consideration is a symmetrical domain. Next, we want to look at the orthogonality relations between sine and cosine function. Okay, so the first integral we want to evaluate is the integral of psi of n pi x over L, going from negative L to L. From the result we get earlier that when you evaluate an odd function over a symmetrical domain, you automatically get 0. So that is the case for the first example. For this example, that we evaluate an odd function, in this case psi function, over a symmetrical domain, this integral will give you 0. So L greater than 0 in this case, and n is a positive integer. So the integral from negative L to L of psi of n pi x over L dx is equal to 0 since we integrate an odd function over a symmetrical domain. Okay. Now moving on to the next example here, we also make the assumptions that capital L is greater than 0 and n is a positive integer. Okay. So the integral is from negative L to L of cosine of n pi x over L dx. Remember, cosine is an even function, so instead of evaluate on the entire domain, I can rewrite this integral as 2 times the integral from 0 to L of cosine of n pi x over L dx. You know, if you remember the technique how to evaluate this cosine function, please go ahead and do it. In this case, the issue is going to be the angle n pi x over L. You can use substitutions to get rid of that n pi x over L. So let me do that. So I let u equal to n pi x over L. So therefore you have du is equal to n pi L dx. Okay. Or if you multiply both sides for L and pi, you get L and pi du dx. Okay. Now, because you make a change in variable, you also have to make the change in the limit of integrations. So I'm gonna make a table here. I have two columns. One is for x, the other one is for u. When x equal to 0, u equal to 0. Right. So this is the relationship right here. When x is equal to L, u is equal to n pi. Okay, so you substitute L into here, and you get L cancel out, and you're left with just u equal to n pi. So the definite integral now becomes 2 times the integral from 0 to n pi of cosine of u times L over n pi du. And L over n pi is the constant, so you can pull that out of the integral operations. You get 2L over n pi times the integral from 0 to n pi of cosine of u du. In the antiderivative of cosine is sine of, so you have 2L over n times sine of u evaluate at 0 and 2 pi, n pi. So you get 2L over n pi times, you evaluate as sine of n pi minus sine of 0. So this is obvious that sine of 0 is equal to 0. Right? And what about sine of n pi? Remember, n is a positive integer, so you can try with n equal to 1. So sine of pi is equal to 0. N equal to 2, sine of 2 pi is equal to 0. So no matter what the value of n, sine of n pi is always give you 0. So the evaluation of this integral will give you 0. Right? So in this evaluation, it just happened that the integral of cosine function is give you 0. It's not always the case, but it just happened in this case. So in the next example, example 7, we would like to evaluate the integral from negative L to L of sine of n pi x over L times cosine of n pi x over L dx. So in this case, we also assume that L is positive and m and n are positive integer. So when you look at the integrand, you have a sine function, which is an odd function, and cosine function is an even function. So the integrand is a product between an odd function and an even function. So therefore, the integrand is an odd function. Now, when you evaluate the integral of an odd function over a symmetrical domain, you will get 0. So in this example, the integral should be equal to 0. So that is the integral from negative L to L of sine of n pi x over L times cosine of n pi x over L dx is equal to 0. The explanation is that since we integrate an odd function over a symmetrical domain. Okay, so that's example 7, very straightforward. Now we're going to move on to example 8. So in this example, it's going to take a little bit of time to evaluate the integral. Because sine is an odd function, sine n pi x over L is an odd function, and sine of n pi x is over L is also an odd function. So a product of two odd functions will give you an even function. So you have to spend a little bit of time to evaluate the integral. So there's no straightforward answer for this particular integral. So in this case, again, we assume that L is greater than 0 and m and n are positive integers. Okay. So we at this point so far we haven't specified the value of m and n. So when you evaluate this integral, you have to break down into two cases. One case when m is equal to n, and the other case when m is different from n. Now you will see by making two distinct cases, the result of the integral will be different. So let's consider the first case. This case when m is equal to n and different from 0. So we have to make that distinctions that is different from 0, because if m equal to n and equal to 0, then psi of 0 is 0, psi of 0 here is also equal to 0, then there's nothing to evaluate for the integral. So we have to make the assumption that m is equal to n and is different from 0. Then the integral becomes, so here I'm just going to rewrite the integral psi of n pi x over L times another psi of n pi x over L dx. Again, remember in this case, we make the assumptions that m is equal to n. So psi of n pi x over L can be replaced with psi of n pi x over L. Now at this point, the integrand can be written as psi square of n pi x over L dx. And there is no basic integral formula that can give you the integral of psi square of something. So you have to manipulate the integrand so that you can arrive at something that is easy to integrate. So we're going to apply something called the double angle identity. So we apply a double angle identity. So here you have a list of some of the formula that you may have seen before. So psi square of theta is equal to 1/2 times 1 minus cosine of 2 theta, and cosine square of theta is equal to 1/2 times 1 plus cosine of 2 theta. Okay, so we're going to apply sine square of theta in this case. So again, sine square of theta is equal to 1/2 times 1 minus cosine of 2 theta. So the integral now becomes the integral from negative L to L of 1/2 times 1 minus cosine of 2 times n pi x over L dx. Now you can distribute, next step, you can distribute 1/2 into the brackets and you get the integral from negative L to L of 1/2 minus 1/2 times cosine of 2 n pi x over L dx. And here from one integral, you can separate to two different integrals. One is the integral from negative L to L of 1/2 dx minus 1/2 times the integral from negative L to L of cosine of 2 n pi x over L dx. So this integral is straightforward to evaluate. This integral, the integral of cosine of 2 n pi x over L, you can use substitutions to reduce the angle, or you can just follow the similar example that we did in example 6 to find the antiderivative of cosine. So here you get, this is 1/2 times x, evaluate at negative L and L, minus 1/2 times L over 2 n pi times psi of 2 n pi x over L, evaluate at negative L and L. All right. So the first term you get, this is 1/2 times L minus negative L minus L over 4n pi. So I combine these two fractions together. Top multiply with top, bottom multiply with bottom. And then I evaluate sine at L and negative L. And I get this is sine of 2n pi L over L minus sine of negative 2n pi L over L. So let me switch to brackets here. Alright. So the first term is simple enough that give you L. So L minus negative L give you 2L divided by 2 is give you L. Now for this term, that you can see the L cancel out, and you're left with sine of 2n pi, so that should give you 0. So here, this should be 0. And for the second terms, the L cancel out as well, and you're left with sine of negative 2n pi, and that one is 0 as well. So in the first case that we analyzed, that we try to evaluate here, we said that m is equal to n and it's different from 0. The integral that we get is equal to L. So we can conclude that the integral in the case of m equal to n different from 0, we obtain that the integral from negative L to L of sine of m pi x over L times sine of n pi x over L dx is equal to L. Okay. You at this point you may wonder that okay, we evaluate an even function here. Should we rewrite the integral to get 2 times the integral from 0 to L instead of evaluate for the whole for the entire domain? I mean, you can. There's no restrictions to that. Answer should give you L as well at the end. The only thing that I care about in terms of evaluating the even or odd functions over the symmetrical domain, it's just that the evaluation or the integral of an odd function over a symmetrical domain give you a more straightforward answer, which is 0. Okay. But for the case of even function, if you want to switch to 2 times the integral from 0 to L and then evaluate the integral, that is totally fine. Or if you want to keep this full domain from negative L to L, then that is fine as well. Okay, so let me move on to the second case. So the second case is where m is different from n. So when m is different from n, we get the original integrals of the form, the integral from negative L to L of sine of m pi x over L times sine of n pi x over L dx. Okay, again, at this point, you see that there's no basic integral formula that give you the integral of sine n pi x over L times another sine of n pi x over L. What you need to do is to manipulate the integrand using another trigonometry identity. So in this case, we're going to apply something called the product to sum identity. So we apply a product to sum identity. So here are the list of the product to sum identities. So cosine of A times cosine of B is equal to 1/2 times cosine of A plus B plus cosine of A minus B. Sine of A times sine of B is equal to 1/2 times cosine of A plus B minus cosine of A minus B. The third one is cosine of A times sine of B is equal to 1/2 times psi of A plus B plus psi of A minus B. And the last one is psi of A times cosine of B. This gives you 1/2 times psi of A plus B minus psi of A minus B. So in our case, where you want to evaluate this product, you need to apply this second identity, the second product to some identity. So I'm going to use a check here to indicate that this is the formula that we're going to apply. So we rewrite the integrand as the integral from negative L to L of 1/2 times cosine of A plus B. So that is m pi x over L plus n pi x over L minus cosine of m pi x over L minus n pi x over L dx. Right. So starting with a product of two sides, you apply a product to some identity, you arrive at a difference of two cosines. Okay. So when you do this, what you do is the next step is to combine the angle together. Right? So you have n pi x over L plus n pi x over L. You have L as a common factor. The common denominator. Now you get the integral from negative L to L of 1/2 times cosine of m plus n pi x altogether divided by L minus cosine of m minus n pi x altogether divided by L dx. All right, so how could I get that? So again, if you combine these two fractions together, you should have m pi x plus n pi x over L. Right, again, for L is the common denominator. Now the next step is to take pi x as a common factor on the numerator, and you're left with m plus n times pi x altogether divided by L. And you follow the same procedure for these two fractions. So hopefully you understand or you see how we get to go from one step to another step, from one step to another step. Okay, let me erase this. Okay, so what is m plus n and what is m minus n? So for m is an integer, n is also an integer, so a sum of two integers should give you an integers. That's going to same to m minus n, so m minus n should give you a integer as well. Okay, so without loss of generality of the problem, so without loss of generality, we assume that m is greater than m, so that when you take the difference will give you a positive integer. And we let that m plus n equal to some p, for p is a positive integer. And m minus n is equal to q, for q is a positive integer. Right, so again, we know that q is a positive integer because of the assumption we just made here, that m is greater than n, so m minus n should give you a positive integer. Now you can rewrite the integral as 1/2 times the integral from negative L to L of cosine of p pi x over L dx minus 1/2 times the integral from negative L to L of cosine of q pi x over L dx. Okay, So either you just use substitutions in all of the basic integral formula to evaluate these two integrals, or you can go back to the previous example that we have, which is example 6. And you see that the integral of cosine of n pi x over L for L going for x going from negative L to L is equal to 0. So you can apply this result, right? We already see the result. We can automatically apply that. And but in our case, you have cosine of p I x over L. It's going to be the same thing because we didn't specify any value of n or p for that matter. So the result that we get in example 6 should easily be applied to whatever we have in example 8. So here, so this one should give you 0, and this one should give you 0 as well because q is a positive integer, and this result can be obtained from example 6. Okay, so therefore, the answer to this integral is 0. So when m is different from n, we get the integral from negative L to L of sine of m pi x over L times sine of n pi x over L dx is equal to 0. Okay, so that's it for example 8. Now, on the next page, I'm going to write the summary of all the results that we get for the integral evaluations. So the first integral evaluation we get is the integral from negative L to L of sine of n pi x over L dx. The argument for this is you evaluate the integral of an odd function over a symmetrical domain, then you get the result to be 0. The second integral result is the integral from negative L to L of cosine of n pi x over L dx. And this one, it just happened to be 0 as well. It's not going to be the case for all the situation. It's just that in this case, we get it to be 0. The third result is the integral from negative L to L of sine of m pi x over L times cosine of n pi x over L dx. And this one is 0 as well. Again, the argument is that you integrate an odd function over a symmetrical domain, you should get the integral to be 0. Now, number 4, we just did, that is the integral from negative L to L of sine of m pi x over L times sine of n pi x over L dx. And there are two cases to this evaluations. The first case is equal to L. In this case, n is equal to m, different from 0. And the second case is the integral equal to 0 when m is different from n. And there is one more integral, but I'm going to leave that for your homework. I'm going to leave that for you to for the homework. We have the integral from negative L to L of cosine of m pi x over L times cosine of n pi x over L dx. And in this evaluations, there are 3 different cases. The integral is equal to 2L when m equal to n equal to 0. The integral is equal to L when m equal to n different from 0. And the integral is equal to 0 when m is different from n. Okay. I will send out the homework at some point. And one of the questions we have is, can you evaluate this integral of cosine times another cosine, and can you break down into 3 different cases? Okay. And all of this integral result will make a lot of sense when we move on to lecture 16 when we talk about the Fourier series expansions. Okay. Now, here are some useful results that you're going to see in lecture 16 and lecture 17. That is, so it is sometimes useful to rewrite sines and cosines of some angle in the following manner. So you have seen some of this already, but let's try to do this again. So in this case, we're going to make an assumption that n is a positive integer. So you have psi of n of pi. So psi of any multiple of pi is going to be equal to 0, right? So n equal to 0, you have psi of 0 is 0. When n equal to 1, you have psi of pi is equal to 0, and so on and so forth. For cosine of n pi, this is equal to -1 to the power n, indicate that the value is equal to +1 when n is even and is equal to -1 when n is odd. Sometimes it's convenient to rewrite cosine of n pi in terms of -1 to the power n. Because again, when you go to lecture 16, when you consider Fourier series expansions of a function, you have to rewrite the function in terms of the infinite series, and sometimes you want to see the alternating series, which is -1 to the power n. So you get one term is positive, the other term is negative, so on and so forth. Okay. Now, when you have psi of 2n plus 1 times pi over 2. So any psi of any odd number of pi over 2, or you can write this as psi of n plus 1/2 times pi is going to be equal to 1 when n is even, and is -1 when n is odd. Okay. So this one go back to the unit circle when you have psi of pi over 2 is equal to 1 and psi of 3 pi over 2 is equal to -1 in that sense, right? So it's alternating between 1 and -1. Now after 3 pi over 2 or 270 degree, you go to 5 pi over 2. So psi of 5 pi over 2, you get back to +1. Psi of 9 pi over 2, you get -1, so on and so forth. But when you take the cosine of an odd number of pi over 2, the answer should be 0. So these are some of the results that's going to be convenient for us in lecture 16 when you get the solutions or get the form in terms of psi of n pi, cosine of n pi, or psi of an odd number of pi over 2, or cosine of odd number of pi over 2. Okay, so that's it for me for this lecture. Please let me know if you have any questions.